Assalamu alaikum dear students. Today we are going to discuss discrete circuit BJT amplifiers part 4, in which we will see the common collector amplifier. The common collector amplifier is also called emitter-follower. Why? We'll see. Already done. Analyze the discrete BJT amplifiers, common emitter with or without emitter resistance, and common base. Now we are going to discuss the common collector amplifier. This one is an example of a common collector amplifier. You can see, since you have NPN transistor, you have to have collector more positive than base to have reverse biased here, and forward biased here would be possible if base is more positive, at least zero point 0.5 to zero point 0.7, then it will be forward bias. So forward, reverse, it will work in active region, right? But when for AC signal the collector is common, then this amplifier will configuration will be called common collector configuration, right? So collector is common for AC, then we have to insert the input through base, because base is available. So once base is available, it will try to be the input port, then output will be collected through emitter. So it did, since the output is collected at the emitter junction, that's why this configuration is also called emitter follower, because emitter has to be followed to get the output voltage. The common collector characteristics is not part of your syllabus, but just let me introduce you for your future use, if any, that here you would be having VEC and here you would be having IC. Then these characteristics curve will be just the reflection at the second quadrant, right? Having the same magnitude as soon as you keep the same VBEs, right? Now to start with, let us introduce a proper statement to let you know how the questions can be asked as far as your scope is concerned. Same, draw the DC load line, find the Q point, find the AC equivalent circuit, and then have these values. Load will be 1 kilo ohm, R signal will be 10 kilo ohm, and so on. Write the expression of voltage expression of AV naught, AV, GV naught, and GV for this amplifier. Calculate the numerical values of all these things. So here what is new is that this amplifier is now common collector amplifier, right? So same DC analysis. For DC equivalent circuit, remove all the capacitors. You will get this, and Thevenin's form of this is this VBB RB. This, for these given values, VBB will be this one and RB will be 20.1 kilo ohm. To find the Q point, we have to write the equation of this loop L1 and this loop L2. L1 will be VBB VRB plus VBE VRE. VRB will be IBRB, VRE will be IERE. By using these relation, we can replace IB by IC by beta and IE by IC by alpha. Then you have IC only. You can arrange it for IC and put VBE is equal to 0.7. Then we will get IC is equal to 5.76 milliampere, because this is called an amplifier circuit. So we are taking VBE is equal to 0.7. So about L2, Kirchhoff voltage about L2, we have only VCC, VCE and VRE, right? So VCC plus VRE will be IERE, and by using this relation, IE can be replaced with by IC by alpha. So now we already have IC. When we put IC here, we have also VCC already given 16 volt. We get VCE Q is equal to 7.9. So this is our Q point. You please draw the DC load line yourself and place the Q point by yourself. AC equivalent circuit and its parameter. To find the AC equivalent circuit, we already know that our capacitors will be short circuited because it is designed for the given signal. And DC sources, voltage sources will be shorted to ground and current sources will be open circuited. We have DC circuit only, so this will be grounded. This will be short circuited, there will be short circuited, then the AC equivalent circuit will be looking like this. Since RB1 and RB2 are coming in parallel, so we can rearrange it for further simplification. Right now, we are ready to analyze ABGV and other things, but only within this circuit, we already said that it is difficult. So it is better to find the model based equivalent circuit. So we can replace this transistor by its model. Which model, pi or T? T will be suitable because we have RE here. Not only RE, we have output collected at the emitter resistance. So how can we use uh, pi? Of course we can use. Then your emitter will not be grounded. You have to place RE and RL, and then you have to reflect the resistances from emitter to base or so on. We have already discussed this with common emitter amplifier with emitter resistance and by using forcefully the pi model. Now comes back to the business. Replace this transistor by its equivalent circuit. Choose to be T model. So now connect the other discrete components attached with this transistor. At the emitter we have emitter resistance and in parallel with RL is available, right? And at the collector we have only ground. AC is grounded here because DC source is grounded, then you have no connection, no other component here, so collector is grounded directly. And at the base you have RB ground and a signal source, a practical signal source, that's why we have an R signal. And the newly introduced parameters will be having a relation this and this. After putting the given values Vt and the computed value IC, IE and VCQ, we got these values, right? Now we are ready to analyze this circuit instead of this one. Why? Because here this is the designed stage given us for analysis, and it is difficult to see what is input resistance, output resistance and so on, but here we can see easily which internal or external resistances are coming in series or in parallel or reflecting at the base, at the emitter and so on, right? So here we already know that if we are going to see at the base into the transistor, it means we are looking the resistances of internal resistance of the transistor while looking at the base, right? So we can see we can have RE here, but it is at the emitter side, so it will be reflected here as 1 plus beta RE. But before doing that, there is not only RE is here, RE is in series with some other things. So let's close it from here and then we can see what is feeling the resistance at the base side. So here we can see these three resistances are parallel. Let me introduce one thing, is that here you have R0 to ground, right? This terminal of R0 is grounded and this terminal of R0 is same as with RE and RL. But other terminal of RL and RE are also grounded, so it means R0 is parallel with RE and RL, right? So now comes back, RE is parallel to R0 and parallel to RL, then these three resistances can be replaced by a single resistance, which will be the parallel combination of these three resistances, right? And then this only one resistance, this one, the parallel combination of this, and this RE is coming in series, right? So it means at the emitter you have this resistance, this total equivalent resistance, right? But when this resistance we want to see into the base, then it will be reflected or feels as 1 plus beta time than it is in emitter, at emitter, right? So at the base side it will be 1 plus beta time higher, right, than the emitter side. Okay, so now we can write the R input. So R input will be RB parallel to this one, RIB, right? And then V input will be at the R input resistance, at the input of the stage. You have Rn and you have Vi will be developing here, right? So V in will be equal to what? The voltage appearing at the input resistance, which is the combination of all these resistances, right? So out of V signal, right? And part of which will be developing here and other remaining part will be here. So it means we have voltage divider by R signal and Rn. So Rin divided by R signal plus Rin into V signal will be the Vi. Simple voltage divider by formula, right? Then how about VBE? So VBE will be a part of V in because V in will be across RB and across this RIB, right? RIB. So RIB is whole resistance here, this one, and this RIB is then distributed into two resistances, this one and the parallel combination of this one, right? We already did these things in intermediate, that you close the resistances, find the voltage and current, and then break down the resistances again to find the current if they are in parallel and to find the voltages if they are in series, right? So this resistance and these resistances are in series and then these resistances are in parallel. So it means part of Vi will be appearing here and part of Vi will be appearing here. So part of Vi appearing here will be the VBE. So we can write VBE is equal to 1 plus, out of this 1 plus beta time RE divided by 1 plus beta time RE plus 1 plus beta time parallel of this, right? And VBE will be, we can also take 1 plus beta common and cut it out to have a simplified formula, right? Then what will be the V output? You see, part of this Vi is developing across VBE, RE, right? Called VBE. And remaining part of this Vi will be appearing across the parallel combination of these resistances. So what it will be? It is V out. So it means RE divided by RE plus this is V into Vi is VBE and V out will be these resistances divided by these resistances plus these resistances into Vi, right? Obviously 1 plus beta and then 1 plus beta will be cancelled out here as well because of having common factor at the numerator and denominator, right? So do we need to find R out to find V out? No, we already know V output here. Why is it so? Because we are not having GM multiplication of VBE to find output. This current source developing at the collector, as far as this model is concerned, is not playing its part. The only thing is RL is reflected at even at the input side, right? You can see it at the input side. And same is the case if you reflect these, if you want to see input resistance at the emitter, then these base resistances, the resistances are connected at the base, will be feeling as 1 plus beta time less. It means RB will be feeling here as RB divided by 1 plus beta, right? We have already discussed these things in comparison with the base current and emitter current, right? So now it means we can see V out is directly found. Another thing is here you can see you have it means you will be having higher input resistance because all these resistances are playing its part to make input resistance. That's why common collector have very high input resistance. It means it is a good amplifier as far as the input impedance is concerned. Same is the case, you have a parallel combination of these and in series with this RE, you are having a very low output resistance, a very good stage as far as output impedance is concerned. So these two qualities are very good as far as this common collector circuit or emitter follower circuit is concerned.